Today, we are diving headfirst into a topic that is, let's be honest, famously weird. It's one of the most successful, most powerful, and most mind-bending theories in all of science: quantum mechanics. This is the rulebook for how the universe works on the tiniest scales, and you're about to see just how strange those rules can get. All right, let's just rewind the clock a bit. Picture it. It's the late 1800s. And physicists, they were feeling pretty smug. They honestly thought they had it all figured out. You had Newton's laws for moving objects, Maxwell's equations for light. Everything had its place, and every phenomenon seemed to have an explanation. Physics, for all intents and purposes, felt finished.
Now, that neat and tidy picture of the universe, that's what we call classical physics. It's the physics of our everyday world, right? Billiard balls, planets, things you can see and touch. It's intuitive. But here's the catch. As scientists started looking closer, zooming way, way down to the world of atoms and electrons, they found a whole new realm. And down there, in the world of quantum physics, the rules weren't just different, they were completely insane.
So yeah, you can probably guess what's coming. That beautiful, perfect picture of classical physics, it was about to slam face first into a brick wall.
I mean, really think about that. What could possibly be so powerful, so fundamentally strange, that it would make scientists question everything they thought they knew and basically start over from scratch? Well, it wasn't some grand new theory that did it. It was the data. The clues started piling up from weird results in the lab. Physicists were seeing things that just made no sense. Things like black body radiation, which is just a fancy way of asking why hot things glow. Or the photoelectric effect, where light could literally knock electrons off a piece of metal. None of this fit the old rules. The game was up. A revolution was coming. And the first shot fired in that revolution was a truly wild idea. What if that fundamental line we draw between particles, like little balls, and waves, like ripples in a pond, what if that whole distinction was just wrong? And this led to one of the cornerstone ideas of quantum mechanics: wave-particle duality. Get this, things like light and even electrons aren't strictly a particle, and they aren't strictly a wave. They're both. At the same time, which one you see it just depends on how you decide to look at it. Yeah, let that sink in for a second. So this all started with light. We knew it was a wave, but new experiments showed it acting like a particle, which we now call a photon. But then a scientist named de Broglie came along with this just beautiful argument. He said, well, nature loves symmetry, right? So if waves can act like particles, why can't it work the other way? Why can't particles, like an electron, a proton, or hey, even you, act like a wave? And this wasn't just some nice thought. He put math to it. The idea is that every single moving particle has a wave associated with it. And the more momentum it has, so the faster it's going, the shorter its wavelength gets. And yes, that means you have a wavelength. It's just so unbelievably, ridiculously tiny that we'll never, ever notice it. But it's there. Okay, so if everything is a sort of wave, that has some really deep and frankly kind of unsettling consequences. It means there are built-in limits to what we can ever know about the universe. Some things are just fundamentally, permanently unknowable. This is the famous Heisenberg uncertainty principle. And here's the part that really trips people up. This isn't about having bad equipment. It's not a technological problem we can solve later. It is a fundamental law baked into the fabric of reality. The universe itself is telling you, sorry, there's a limit to what I'll let you know. So let's take the most famous example to really get what this means. Imagine you have an electron and you want to know exactly where it is. You can measure its position really, really precisely. You can pinpoint it. But the very act of knowing its position so well means you have to give up knowing its momentum. You'll know where it is, but you'll have no idea where it's going. And it works the other way too. Know its momentum perfectly, and its position becomes a complete blur. It's a cosmic trade-off. You can't have both. And this isn't just about position and momentum. It applies to other pairs of properties too, like energy and time. The more precisely you know the energy of an event, for example, the less you know about how long that event lasts. It's a universal principle. Okay, so if we can't know anything with 100% certainty, are we just sunk? What can we know? Well, this forced physicists to invent a completely new way of describing the world, and they called it the wave function. The wave function, usually written with the Greek letter psi, is basically the star of the quantum show. It's a mathematical object that holds every single piece of information you are allowed to know about a particle. But here's the key. It doesn't tell you where the particle is. It tells you the probability of finding it in any particular place if you were to look. So a better way to think about a particle isn't as a tiny little ball, but as this smeared out wave of possibilities, a probability wave. The wave is higher in the spots where the particle is more likely to be found, and it's lower in the spots where it's less likely. Before you look, it's all just probabilities. So what tells this probability wave how to behave? What guides its motion and evolution? Well, it's all governed by this one legendary master equation, the Schrödinger equation. Don't worry about the symbols, just think of it as the ultimate rulebook for reality. You tell it the situation, and it tells you how the probability wave will behave. All right, I know what you're thinking. Probability waves, rule books, this all feels pretty abstract, right? So let's make it real. Let's take these new rules and apply them to one of the most classic problems in quantum mechanics, the particle in a box. And this isn't just a brain teaser, it's how we start to understand things like electrons inside an atom. So here's the setup. Imagine an electron trapped in a tiny box. It can't escape. Now, classically, you'd think, okay, it can be anywhere in there with any amount of energy it wants. Simple enough. But what does our new quantum rulebook, the Schrödinger equation, have to say about this? Well, when you solve the math, the answers you get are just bizarre. They completely shatter our intuition. First, the particle can't have any energy. It can only have specific, discrete energy levels, like rungs on a ladder, and nothing in between. Second, it can never, ever have zero energy. There's a minimum energy it must always have. And third, it's not equally likely to be found anywhere. There are hot spots. Now, the really weird part is where you find it. At its lowest possible energy, the ground state, its probability wave is just one big hump. That means you're most likely to find the particle right smack in the middle of the box. Okay? Fine. That seems sort of reasonable. But now, let's bump the particle up to the very next energy level. Suddenly, the probability wave has two humps with a dead spot, a zero right in the center. So by giving it more energy, you've now made it impossible to ever find it in the middle. Wait a second. How does it get from the left side to the right side if it can't ever exist in the center? Exactly. Welcome to quantum mechanics. And that brings us to the big final question. This particle in a box might seem like a simple problem, but it shows us something incredibly deep about our universe. At its most fundamental level, reality isn't about solid objects in definite places. It's about waves of probability and steps of energy. It's a world built on chance. So if the very foundation of everything is just a game of probabilities, is anything, anywhere truly certain?